All right, today we're going to talk about correlation and how we use correlation for analysis or reviewing different types of data. We'll find how effective it is, how important it is, as well as some of the weaknesses that are associated with correlation. Correlation really looks at the similarities or the deviation, if you want to consider it the opposite effect, between just two different variables. The problem is if there are pretty significant differences, both positive and negative. So if you have numbers that are very, very negative, there's a negative correlation between two, and there's a huge positive correlation between the two. Those two deviations will eventually cancel out, and that will really hinder your ability to really understand the relationship between those two variables. It also doesn't really tell us too much about the relationship between those variables. It's going to tell us a few things. It's going to tell us whether it's a positive or a negative relationship, whether it's weak or strong, but it can't really tell us any causality between those two variables, which is really in engineering more so what we want to know. Is there a definite connection? If we increase the value of one, will the other value increase? And by what amount will it increase? And that's not something that we're going to get from correlation. We'll just know that, yeah, if you increase one, the other one will also increase. So there are some limitations to correlation. Well, correlation is, we'll see, really moves on into regression, and there are some relationships between correlation and regression. So what is correlation? Again, we just want to figure out how are two variables related. So what it's going to do is going to look at the relationships or the pattern of responses between an X and a Y pair. Scatter plots are the main basis of correlation and why we can figure out what is going on with that correlation. Scatter plots is just plotting one variable on the x-axis, the second variable on the y-axis, throwing your data points up there, and then we'll be able to analyze how those data points relate to each other. So it just provides a really nice picture of that relationship. Some important pieces about the scatter plot. It's going to tell us slope. It's going to tell us what type of relationship that is. So we'll have either a positive slope or a negative slope. And then the width of the ellipse, how closely those points are tied to a line, will tell us whether that is a strong relationship or a very weak relationship. Obviously, the narrower the ellipse is, the stronger that relationship is. If the points are widely spread out, it's probably not a very strong relationship at all, if any. Nice example of what we have in terms of the scatter plots and the types of relationships. This scatter plot in the upper right corner, if you think about it, what type of relationship is that? Well, it's really not that much of a relationship. I would even question whether there is even a relationship, but we could say there's some type of a minor relationship there. The one on the bottom left over here, that is a positive relationship because the line is going up and to the right. So that's a positive relationship, and you see this ellipse here. It's somewhat of a strong relationship, but it's not nearly as strong as others, but it definitely is a positive relationship. The graph, the scatter plot on the bottom right, it's down and to the right, which means that is a negative relationship. And when you look at this, the scatter plot, the width of that ellipse is really nice and tight, so we could say that is a strong negative relationship. And that's essentially pretty much all you can kind of tell from the scatter plots. And then we'll use the correlational aspects to be able to really decide if it truly is an effect. So correlation, we're just, again, if it is a positive relationship, as one variable increases, the other will also increase. If it's a negative relationship, if one variable decreases, the other will also decrease. Or the variables can stay the same. If one changes and there's a very minor relationship, the other variable would not change. It would stay the same. And that is the essence, that's all we can really tell from correlation, which is one of, again, its downfalls. So how do we determine how strong these relationships are? Well, that's where the covariance is going to come in. And what covariance looks at is how each data point deviates from the mean of that sample. So if you look at just your x variables, it calculate the mean, and then we'll look at how that data point, each data point in that scatter plot deviates from that mean. If both variables deviate from their individual mean by the same amount, they're probably going to be related. And that's essentially how the covariance is arrived at. Or at least you looked before about variance. Covariance is similar to variance. The variance is how much the data deviates from a mean for a single variable, which is similar to the sum of squares. And the covariance is very similar, except we're looking at how much two variables differ from their respective means and looking at that comparison between the two. So when we talked about variance before, very, very similar to covariance. How do we calculate the covariance? A couple little steps. Calculate the error between the mean and each individual variable on the x-coordinate. We're also going to do that on the y-coordinate. You multiply those error values together, and then you sum all of those x's and y's, and you divide by the sample size divided by 1. And so that's how you arrive at your covariance. We're not going to be doing any manual calculations with covariance. That's really not the point of this class. The point of this class is to help you understand how to utilize a software package to be able to calculate this information, but that is how the covariance is arrived at. Now you can kind of look and see that we probably have a problem with the covariance. Definitely depends upon the units of the measurement. So if you look at two different variables, say one is measured in miles and one is measured in kilometers, they can have different covariance values. One could be 4.25 and one could be 11. But it's the same data. But the covariance would indicate that the miles is a much better covariance maybe than the kilometers. But we know that cannot be true because it's just simply the same data that was transformed. So the problem is we just can't compare any covariances objectively. And because of that, you standardize the covariance. And how we standardize it is we divide covariance by the standard deviations for both variables. And this is then called the correlation coefficient, pretty much unaffected by the units of measurement, so we can compare objects. Technically, it's called the Pearson correlation coefficient. Sometimes it has other names, but we're going to just refer to it as the Pearson correlation coefficient or just the correlation coefficient. And you can see here is the resulting answer, just the standard deviations for x and y on the bottom part in the denominator. Again, we don't need to know this equation, just wanted to show you where it is and why we have the difference and why we standardize things. So the correlation coefficient is really what we're going to be looking at to be able to compare one group of data to another group of data and find out which variable has more impact on another variable. Correlation coefficient has to range between -1 and 1. If you receive a different value, you might want to check your calculation. Thankfully, SPSS is going to help you out with that, so you don't have to worry about it. But if you did do it manually, you know that something's wrong in your calculations and you need to go back and check your math. If you have a +1, two variables are perfectly positively correlated. As one variable increases, the other one increases by a proportionate amount. And here's one of the downfalls with correlation. The proportionate amount, we don't know what that means. So just a minor problem, minor downfall of correlation. We don't know what that proportionate amount is. Likewise, a -1, two variables are perfectly negatively correlated. As one variable decreases, the other decreases by a proportionate amount. If you end up with a Pearson correlation coefficient of 0, there's absolutely no linear relationship. One variable increases or decreases, the other one does not change. And any scale value that you use the correlation coefficient is really the ordinal. It's not a continuous value. We can only compare correlation coefficients to each other in a sense that, a 0.2 correlation is not as good as a 0.9, but there's no relationship really between the 0.2 and the 0.9. It's more ordinal. So if you think of it more like, in college where you have freshmen, sophomores, juniors, and seniors, 0.2 is probably a freshman, 0.9 could be a junior or a senior, but we cannot say that 0.9 is 4 times better than a 0.2. We just can't do that. Moving on, kind of a little bit of an interpretation of what all these correlation values mean, and these are absolute values, so they work for either positive or negative values. Very high correlation all the way down to very low correlation. If it's ranging 0.0 to 0.3, you probably don't even have any type of relationship. You might as well skip it. But at least from 0.3 on, you've got some correlation. 0.3 to 0.5 is rather useless at this point. But it's also an effect size, and we're going to get into effect size more so when we get to other tests, the ANOVAs, the t-test. We're going to start calculating effect sizes to be able to tell, when you do a t-test, the results of that t-test, how practical is it? And that's where this correlation coefficient will come into play again, because if it's very practical, we're going to end up with a large effect size. So that means it could be statistically significant and have a large effect, which means that is a very important relationship. However, if it's statistically significant and you have a small effect size, there's really no practical difference between the two. So a good example of this is if the speed limit, let's say, is 65 miles an hour, and we have an 85th percentile speed of 67 miles per hour. We could say, depending upon the sample size that we have, that's a statistically significant difference. But practical 2 miles an hour is not really kind of what we're looking for in the real world in terms of a difference. If we're trying to reduce speeds or increase speeds, we're looking on the ranges of 5 to 10 miles an hour, not 2. So that's another nice way to think about how important is the statistical significance, is looking through this effect size. So we'll use this quite frequently as we go through the rest of the semester. All right, what assumptions do we have with the data that we use and want to analyze using correlation? Well, we have to have paired observations. Obviously, there's X and Y's. You can't create a scatter plot unless everything is paired. The variables that we're looking at have to be on an interval or a ratio scale. They cannot be categorical. And then to determine significance, whether it truly is relatable or not, we need some type of normal data. And for that normal data, you'll refer back to your statistical analysis sections. Again, looking at that probability plots, your histogram. You can look at the z-scores for your skewness and your kurtosis. Again, I would not recommend running normality tests like the Komalno-Smirnov or the Shapiro-Wilk, simply because the more tests you run on your data, the weaker the power is, and that's not something that we were wanting to go for. What affects the size of our correlation? Obviously, linearity. Correlation only looks at linear data and not look at curvilinear relationships. We can, but the problem is that the resulting analysis will not be able to tell us whether that is a true curvilinear relationship. We also need to have some type of homogeneity of the sample, which means as everything becomes very, very similar, that correlation coefficient is going to start to decrease. So we have to have enough variation to make sure that we can have a relationship, but we don't want to have them be so different that it just doesn't make sense. One of the things that you can do a correlation between, I remember seeing it online a couple months ago, the number of doctoral degrees issued is correlated with the amount of cheese eaten at like a 0.9 correlation. Okay, well, there's clearly enough variation in that data set to show a relationship, but there's really no relationship between the number of civil engineering PhDs and the amount of cheese eaten. So if everyone stops eating cheese, no one will graduate with a PhD in civil engineering. Well, that's ridiculous. So you have to make sure not only is it homogeneous, but that it makes sense, that there should be a relationship between the two variables. The size of the sample doesn't really affect the size of the correlation, but it will affect the accuracy of the correlation. Though a very, very small sample size will impact the accuracy. We would like to have a fairly decent sample size, and 100 is a really nice value for pretty much anything, but there's equations that you can look out to figure out what sample size we should be having. Is the correlation coefficient squared, which makes it the coefficient of determination. So that's the proportion of variance in one variable as it relates to another variable. And that's really going to be able to tell us more accurately how the correlation between these two variables work. And we'll get to an example of this a little bit later. The Spearman's rho, the Pearson correlation can only be used for interval data. If you do not have interval data and you have ranked data, you can use either the Spearman's rho or Kendall-Tau. Kendall-Tau is a little bit different, again for ranked data, but it's much better than Spearman's rho if you have really small samples. And if you're ranking your data, you could have some ties, like anything in sports, you have ties. So we can have the same thing with any data. So Kendall-Tau's is nice to be able to match if you've got a small sample or something with ties.